So next we'll be hearing from Kaul on the survival and growth of infalling cold streams and clouds with magnetic fields in the CGM.
So, hi everyone. I'm Ish from UCSB. I'm finishing my second year as a grad student, working with Brent and Pengo for this project. So I'll talk to you a bit about what magnetic fields do in cold cloud and cold stream infall in the CGM and onto the galactic disk. So we've already heard about this, so I'll not spend much time on it. But the basic idea is that there's two possible ways in which you can get star formation in the disk. Well, you need to replenish the cold gas for star formation. One of the ways is you can launch galactic outflows and then the clouds fall back down. That's my little cartoon that I made. And the other way is that you can have cold streams that are accreting. So these trace galactic, like large dark matter filaments, and those can eventually get cold gas down into the disk at the bottom. And this has been confirmed. Well, it was first found by Avishai Decker, but it has then since been confirmed with a lot of other simulations. There's more data coming that we're not entirely sure if streams do exist, but there seem to be more data in the past few years that there might be streams like these. So this is why it's important to really zoom into both of these processes, one which is cold cloud infall and the other which is cold stream infall, to really figure out how do the dynamics of both of these things work, because that really is understanding how star formation and how galaxies evolve. So a basic overview about what cloud crushing means. So these simulations have been done for the past 30 years, and it's basically just a cold cloud that's embedded in a hot wind. And you're really trying to see what makes the cloud survive and what destroys it. So the broad consensus is that there's a competition between two time scales. Sorry, my bad. One is the cloud crushing time, and one is the cooling time of the mixed gas between the cold cloud interface and the hot background interface. And so if your T-cool mix is shorter, then the cloud generally survives. If it's longer, then it's going to get destroyed. But really what happens when you include gravity, so when you're trying to figure out, when you're following a cloud as it falls down under the influence of gravity, instead of T-cool mix, the relevant parameter is T-grow, which is far more stringent. So the T-grow and TCC criteria is actually the sufficient it is the necessary and sufficient criteria in this case. And it's more stringent than just the T-cool mix and TCC criteria. So what do I really mean by T-grow? It's just the growth timescale of the cold mass in the cloud as it falls through the CGM. So these are just the equations we use to model it. The important thing here is this equation, because what this is telling you, it's sort of like the opposite of what happens in a rocket, where because you're adding more mass into the cold cloud, you get this additional braking term, which slows down the cloud as it falls through, which will turn out to be important, as you'll see. So we do 3D MHD simulations of this in Athena++, and I include magnetic fields to see what does that imply. So here's what I find. The rightmost plot shows you the evolution of the cold mass as it falls through over the course of almost 200 million years. And as you see, so beta is the plasma parameter, which is the ratio of the thermal pressure to the magnetic pressure. So lowering beta means you're increasing the magnetic field. So you see that as you increase the magnetic field, or as you are lowering beta, you get marginally less cold gas in the cloud, but you still get survival. So cases where you have survival stay the same, you just have this, another way to interpret this is using T-grow. You can find out what the slopes are, and that's what you get. So you'll see that as you are lowering beta, you get slightly higher T-grows. But if you look at this dashed line, this is just from the hydro simulation and the model that we use to model hydro evolution. It's roughly the same. It doesn't matter as much. The other thing you'll see is that the accretion braking effect, which is what I mentioned, that the cloud slows down as it falls. Again, you can see, unless you go to beta of 1, which is like an exception, you sort of asymptote towards the terminal velocity. So the lower you have beta, the more, the higher you get T-grow, which means that you have the mass growth being suppressed by around the same factor. So to really examine what is happening with magnetic fields, if you notice this plot, this plot really is showing you what the inflow velocity looks like. So why do I care about inflow velocities in the first place? This is how mixing proceeds, or this is how cooling proceeds. The hot gas basically interacts with the cold stuff in the cloud and causes it to like mix and become at this get at this intermediate temperature. And then this intermediate temperature then cools because you have radiative cooling in the simulations, and then attaches itself to the cloud. And that causes that looks like an inflow velocity, which is why you have this happening, as you see. This is a simulation of beta of 100. You can see that's like the full cloud. It develops this long tail. But what happens is when you actually get to beta of 10, you'll see this gets actually a little suppressed. So you can see there's lower inflow velocities. Why should that even happen? It's because magnetic field lines, so mind you, this is with aligned magnetic fields. Why should that happen? Well, because if you have aligned magnetic fields in the first place, you have this thing called magnetic tension, which you just get from ideal MHD, which is that these magnetic field lines try to act like a wall, so they don't want to bend, which is why you get suppressed mass growth. The other thing you'll notice is that you get this really long tail, which you didn't have before, and you can see at the tail end of it, there's actually not a lot of cooling happening. Most of the cooling only happens in the head of the cloud, well, contrasted with this picture where the cooling was happening throughout the entire body. And interestingly, the whole tail is mostly supported by magnetic field. It's mostly supported by magnetic pressure. Whereas like at the head, you have like some combination of thermal and magnetic pressure is happening. So you can make this a little bit more quantitative. You can see as you're lowering beta, you go down in turbulent velocity. And using some simple arguments, you can show this scaling exists between the mass growth or the change in the cold gas mass and in turbulent velocity, and it follows this relationship. This has nothing to do with magnetic fields. But when you do add magnetic fields, you see that this relation actually stays the same. This is something that has also been seen in just purely cloud-wind interactions. This scaling remains the same even throughout that. So all that this is telling you is that because you have reduced turbulent velocities, by turbulent velocity I mean in the x and y directions, you get reduced mass growth by that exact same relation, which holds across. So what does that mean for their survival? This is where things get a little tricky. If you have aligned fields, which is the story I was trying to show you, stuff remains pretty much similar. If the cloud is dying in hydro, this dashed line is the hydro criteria. Everything above this in hydro will survive. Everything below this line will die if it's hydro. That is roughly the same if you have aligned magnetic fields. That is not the case with transverse magnetic fields. Transverse magnetic fields are their own beast. And the reason this is different is because with transverse magnetic fields, you actually become even slower because now magnetic tension is in the medium. And in the medium, it's trying to make the cloud fall way slower. And you can see this, the lower beta you get to, the slower and slower your cloud is falling. And really what that does is because your cloud is slowed down so much, cooling can just make it cool to like, cooling becomes like so effective that it just makes all clouds like survive to some extent, which is why transverse fields are a whole different thing. But what does this mean for streams? So Neil Mandelker showed that instead of T grow, Neil Mandelker showed that instead of TCC, which is the cloud crushing time, the disruption time scale here is something called TSH, which holds pretty well for like transonic flows. If you go to highly supersonic, it does not work as well. But really, streams should not go sub-supersonic in the first place. At least that's what the cosmological simulators will tell you. So this is just a modification of that, the equations that I had for the cloud. But here the difference is we're looking at profiles instead of the time evolution. Because we thought that if you actually inject cold gas from the top of the box, instead of looking at a stream that's already there and then evolving it, it turns out that this is a more realistic setup. For reasons you can talk to me about at some point later. But here what you see is that with just the hydro case and our model, you get this upturn at the end where it's, so at this point it's in free fall, but then here it starts to go up. The line mass is just, you can think of it as a mass as it's going down. And then magnetic fields are an interesting story. When you have aligned fields, there's suppression in mass growth, so you get this. If you have transverse fields, it's a whole different thing. I can skip over that. But this is basically telling you this part is free fall, that curve, and the magnetic field case is close to it. But if you have hydro, you sort of reach try to reach some turbulent velocity, some asymptotic terminal velocity. So what does that mean for its survival? Is it the same as clouds? It turns out it seems like it is, yes. Because if you really look at the t-grow for the streams and the disruption time scale, you see that whenever t-grow goes below the shearing time, you get growth, which means that you can apply the same criteria for streams as well. This is valid up to a factor of like 2 or 3, which is, we're not sure where that comes from, but it's pretty close to having that. And well, we did this for a realistic halo profile, which is probably more relevant to us. So this was like using Ong et al.'s equations, which was, it was close to an NFW profile, and you can derive with hydrostatic conditions, you can get the temperature profile and the gravitation profile. And you see that a similar relationship holds. The gas mass gets to like about half by the time it reaches 0.1 virial radius, 0.1 virial radii, but it still survives, even though it shows it. Well, the criteria does tell you that it's probably going to die, but it survives up to this point because it's like fast enough to reach there at that point, so it does survive by then. And yeah, I'll leave the conclusions up.
Questions? Yes.
So I'll ask about your the thing that you mentioned that someone should ask you about. Why is it a more realistic setup when you are sort of injecting the cold gas instead of already having a stream there?
Right. So when you already have a stream and you say have like periodic boundary conditions on both sides and you just let it fall, it quickly becomes supersonic. And by supersonic I mean like Mach 6 to Mach 10. And you don't want that to happen. That's just because cooling is not efficient enough for a stream for that to happen. And the reason why that is, like, if you have a cloud that falls, it develops this tail, right? So you have more surface area for cooling to happen. In a stream, it doesn't. There's no place to extend. So it's not that effective. And in any case, in a realistic situation, you probably have something like a stream that's like going in, as opposed to a stream that's already there and it starts to fall. So it's more realistic in that sense. Yeah.
Other questions? Okay.
So for your last point that you were making about the stream surviving all the way through, in at least some cosmological simulations I've seen, that doesn't seem to be the case. They don't connect directly with the disk. I'm wondering if you thought about, is it something to do with like feedback or something that's included in those simulations but not in what you've done?
Yeah, it could be. So the only things that we have here are just radiative cooling and magnetic fields. It's possible that if you have other feedback processes, if you maybe even have like a turbulent background, it might disrupt it even more. It's possible. But we haven't looked at that yet. But it's possible, yeah. Yeah.
We have time for another question. There is one? Yes, and maybe the next speaker can start.
So you mentioned that with magnetic fields you have slightly slower growth rate initially. Have you checked what happens at the later stage when you have the more or less co-moving with the surrounding wind?
Yes. So we don't actually co-move because in gravity there's no like, there's always a continuous shear here, right? So you're never actually co-moving with anything. You're always continuously accelerating.
So you reach terminal velocity.
Yeah, until you reach a terminal velocity, exactly. Yeah.
Okay, let's thank the speaker.